Hi, my name is Gwen, and I am the founder of Eve Quantum Systems in Singapore. So, why quantum? We are actually discussing this as a framework for kind of like the future of computing and cryptography. And I find that people are getting more and more interested. And because of that, that's why we have this full series. So, if you have questions or if you kind of even want to explore quantum as a student, come and talk to us. My email is down below, and we are very happy to welcome even people who are looking at creating quantum resilience for the business. So, today we're laying the foundation for our entire journey through quantum computing. We're deconstructing the first chapter of Nielsen and Chuang, not just to define terms, but to understand the why, the historical collision of physics and computation that created this field. And by the end of this, you understand why the qubit is the most significant pivot point in the history of information. So, why spend time on this? Because actually, for decades, scientists have asked, can we use the laws of quantum mechanics, the most accurate rules of the universe, to process information? So, this field was actually born from three crises. Classical physics couldn't explain the quantum world. Classical computer science hit a wall trying to simulate nature, and our standard cryptographic systems were built on assumptions that ignored physics. So, quantum information science is the collision of these three failures and the solution for them. This brings us to the breakthrough. In the 80s, Feynman realized to simulate quantum physics, we need a quantum computer. Then Shor proved that we could break encryption, and this is a massive wake up call. We realized that our biggest enemy was noise, or also known as entropy. And if we could manage that noise with quantum error correction, we wouldn't just have a novelty, we'd have a new kind of machine. So if we need a new machine, we also need a new building block. And the qubit, the superstar of it all, there's many videos on the qubit. So I'm gonna be very light on this one, just because you guys can probably find hundreds of videos explaining just that. And it is a unit vector in a complex space. It's one, it's zero, it's maybe one or zero all at the same time. It exists in superposition, so it isn't just more information, it's a completely different geometry of possibility. But why is this a game changer? Because of the exponential leap. If one qubit is interesting, multiple qubits are where the magic happens. So as your qubits are added, the state space grows exponentially. So with just 500 qubits, you're dealing with more possibilities than there are actually atoms in the known universe. And this is the engine of quantum power. If the qubit is our data, gates are the verbs. They are the actions we take. So unlike classical computing, where gates are often irreversible, they destroy information. Quantum gates are unitary transformations. They are reversible. This means that if you know the output, you can trace the steps back to the input. And this is a fundamental shift in how we handle logic. So, how do we turn these gates into actual solutions? We use them to build algorithms. A quantum computer's real advantage isn't just speed, it's a unique way to handle massive problems by evaluating functions in ways a classical computer never could. So, we use techniques like quantum parallelism, putting inputs into superposition, and then use interference to make sure that the right answer stands out when we finally measure it. So, we close this chapter with quantum information theory. It's the physics of the possible. It defines the hard limits of what we can communicate and store. It treats entanglement and qubits like a precious resource, things that we can measure, trade, and spend to solve the world's most complex problems. And in chapter two, we're actually going to define the rules. We'll start seeing how they behave in the physical world. And finally, why does this even matter for business? Why does this matter in the boardroom? So we're moving from an era of brute force classical computing to quantum enhanced strategy. The business applications of quantum information science fall into three critical pillars. First, optimization. You move beyond simple linear regression to solve complex portfolio risk or supply chain logistics where variables are nonlinear. And secondly, simulation. We're talking about accurate molecular modeling for drug discovery, tasks that are essentially impossible for classical computers to compute in our lifetime. And third, machine learning acceleration. using quantum systems to identify hidden correlations in data that current neural networks miss. We aren't just making things faster, we are making the intractable computable.